The second way to multiply two vectors is called the cross product. Unlike the scalar answer we get with a dot product, when we do a cross product of two vectors, we actually get a vector as an answer. So we need to know both its magnitude and its direction. So two things we know about its direction is, first of all, if we do A cross B, the resultant vector, the cross product of those two, is perpendicular to both A and B. So if we imagined A and B on a piece of paper, so let me draw a piece of paper here. This is a piece of paper, and A and B are both on this piece of paper. That means vector A cross B is sticking out perpendicular to both of those vectors off of that piece of paper. And I don't know if you can picture that very well in two dimensions, but that is the vector that is perpendicular to both A and B. Secondly, we know that the magnitude of A cross B is the magnitude of A times the magnitude of B times sine of theta, where theta is the angle between the two vectors when they're placed tail to tail. So very similar to the dot product in this regard, but instead of being the cross product, this is the magnitude of the cross product. So this tells us how long the vector is. Also, we need to know when A cross B is perpendicular to this piece of paper that has A and B drawn on it, which way is it sticking out? Is it sticking out above the paper or below the paper? So which way does it go? And this is determined by something called the right-hand rule. And I can't demonstrate the right-hand rule very effectively on the video because you can't see my hand, but we'll do this tomorrow in class and talk about this a little more. But look at the drawing on the left-hand side here, and imagine when I do A cross B, imagine taking your fingers, positioning your right hand. And by the way, if you try to do this with your left hand, it won't work. That's why it's called the right-hand rule. You have to use your right hand. Imagine positioning your hand in such a way that as your fingers curl, they're pushing vector A towards vector B. So if you picture pushing vector A towards vector B with your fingers, the thumb will point in the direction of the vector that is the cross product. Now, if you do B times A, notice you're going to have to turn your hand upside down to do that. To push B into A, you're going to have to turn your hand upside down. And when you push B into A, your thumb is pointing down. So rotating from B to A creates a different vector product than rotating from A to B. So A cross B and B cross A are not equal to each other. Now, this has implications for a 3D coordinate plane, because if we imagine using the vectors I, J, and K, remember they're all little vectors of unit 1 that are served as the basis of our components for our vectors. If we were to cross I cross J, so you have to kind of imagine holding your right hand in such a way that you're pushing I towards J with your fingers as they curl, you'll notice your thumb will push straight up for vector K. So I cross J is equal to K, which is this middle, the top one in the middle row. If you can position your hand in such a way that your curl of your hand is pushing J onto K,